We can look at a lot of these. Let's look at 19 to start off with. How many ways are there to put 4 tires on a car? This question should be asked from the perspective of mechanics are not important, because if you're really putting tires on a car, there's a very specific way they put them on. Like, especially if they're rotating your tires, like you don't want to like actually like just rotate them one rotation worth. Like you actually have to like the front ones in the back and the back ones in the front, and like so. But if you are just putting 4 tires on the car any which way, well, you can put the first tire anywhere, and then the second tire any of the remaining spots, and then the third tire any of the remaining spots, and then the fourth tire any of the remaining spots. And since each spot is different, right, we don't have to like divide by anything. We're just going to get 4 factorial. So some of these problems do require you to kind of forget about your real world common sense some of the time, because that's not what the probability is actually asking about. Let's look at 20. Not this pen. So 3 cars arrive simultaneously. Simultaneously, I just want to put an extra L in it. Oh, well, I spelled simultaneously incorrectly before. I'll do it again. At a 4-way stop. And all want to go straight. How many ways can this happen if they all go one at a time? Feels like a weird question.
I think this is a combination one, because it's like the 3-car 4-way stop, 4-way, and the 4-way one is not relevant. I think it was relevant.
Yeah, I'm not sure. Like, I think you're right, but let's. So I would draw a picture. So I've got my like 4-way stop, and here's like car A, car B, and car C. So I feel like this is just another factorial answer. Like my guess would be, well, first, who goes first? Well, there's 3 choices, car A, B, or C. Who goes second? Well, there's 2 choices, whichever, right, of the cars remaining, pick one of those 2. And then who goes last? Well, whoever's left, there's only 1 choice. So I feel like the answer here would be 3 factorial. Yeah, it's kind of funky though. I wish I could see the answer. I don't know. I don't think we have. Yeah, I don't think we have a copy of the solutions to this. I'm curious about 12.1 number 1 though. Number 19. Okay, we did number 19 correctly. Right, that's reassuring. Sometimes it is all about like interpretation though. Like maybe if you were talking about like we care about which direction the cars came from, right? Like maybe, you know, how many different ways can it happen if we want the cars coming, you know, not from the right or not from the left or not right. That could be an additional thing to factor in there, but I don't feel like that's what the question is getting at. Sure. It's always hard to keep track of where I am. So let's look at a couple more of these. Let's look at 23. Which I feel like, again, some of the phrasing of these questions just makes it feel like, what are you really saying? Obtain a formula for the number of permutations of n objects when taken k at a time if a particular object must never be included. So what does this say? So here's what I think it says. We're permuting K objects out of how many? Well, yeah, n, but really I would say it's kind of out of n minus 1, right? Because they're saying we're going to obtain a formula for the number of permutations of n objects when taking K. Right? This is phrased so badly, I feel like. Permuting n objects when taking K at a time if a particular object must never be included. So what I'm really trying to do is let's look at an example, because like these numbers or these lack of numbers, I think make this more challenging. So let's say we want to do the following. We want to permute, and again, I'm going to use their language, even though I feel like it's not great. We're going to permute 10 objects when taken 4 at a time if a particular object must never be included. So let's think about that. So if I'm permuting 10 objects I see, like, if I'm reading this, I feel like I guess I am permuting 10 objects. Okay, that's fine. So I'm taking a group of 4 things. And I want to know how many permutations there can be of these 10. Well, except I have to not have one of them every time. So really, if I'm permuting 4 things, I've got 4 spots. How many choices are there for my first spot? I get a hint, it's not 10. It's not 10 because one of them must never be included. So like of these 10 objects, right? Sorry.
That next to that must that you
Never.
Okay.
I know. Problem is I try to write fast and then things don't look good. So if one object must never be included, we really only have 9 things to choose from. So there's 9 choices for my first spot. And then there's 8 choices for my second spot, 7 for my third, and 6 for my fourth. To me, this is looking like 9 factorial over 5 factorial. If that's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over. Well, so let me answer your question with because we have 9 factorial over 9 minus 4 factorial. Basically, you want the factorial on top, and then you want to cancel out all the terms after you've done the first 4 of them. So this 9 factorial on top gives me 9, 8, 7, 6, 5, 4, 3, 2, 1, 7, right? And then the 9 minus 4 says, okay, take your 9, give yourself the first 4 terms, but then after that, everything else is going to go away. So these all cancel. Does that seem sensible? Okay. So then if we go back to this, instead of using, so what I would really do if I was doing this, I'd be like, okay, instead of using 10 and 4, I really want to be using N and K. So this formula looks like instead of 10 giving me 9, I'm going to have N giving me N minus 1. And instead of, whoops, I don't want a fraction. I don't want that either. Fine. I'll just write the formula. So I want N minus 1 factorial. And instead of 9 minus 4, I really want N minus 1 minus K. Check. Bless you. And that's exactly the formula. But I do think it made it easier to see by actually picking real numbers. Like, and this is a common tactic, right? If you're seeing like, I'm not sure how to do this actual formula, throw some real numbers at it. I will say my choice of numbers might not have been great in that when I was getting here, it might have been a little confusing, like where the 5 was exactly coming from. It might have been good to pick numbers that were a little further apart from each other, or that the 5 wasn't so quite in the middle of 9, kind of. So it might have been better to do like, something more like, I don't know, 15 and 6 might have been a slightly better choice to kind of see what was going on, but it still works.
How is it 9 instead of 10?
So because they said a particular object must never be included. So from the group of 10 things, one of them was always like, basically they should have just said your group really only has n-1 things. They were just trying to be kind of circuitous about it. They were trying to hide information to make you think about what you had to do. Let's look at number 26. A mate choice experiment. Okay, choosing mates is conducted. Oh yeah, I was helping someone with this problem earlier, and I was like, I'm not sure if that's a typo for the word child or if that's an actual thing, but I think it's an actual thing.
Oh,
What's that?
it's a fish.
Okay, but I thought it was actually like I thought they misspelled the word like child. I was like, is that a typo or is that like a thing that I don't know about? And it's clearly a thing I don't know about. So, in which, yeah, a female chillid.
Yeah, I had to deal with a fish in bio.
Interesting. Really? I mean, I probably have seen one, but wouldn't know it. So a female chillid, learned something new today, is allowed to exhibit her preference for each of n different males. How many rankings are possible? I feel like a lot of these questions are just trying to reinforce the idea of how a factorial works. So this female chillid has n males to choose from, and she's going to rank them all from best to worst. So how many possible choices are there for the best male? Well, how many chillids are there? How many chillids are there? I should say, how many male chillids are there? Yeah. So we have n choices for the best male. Maybe she thinks it's that guy. Maybe she thinks it's that guy. Who knows? But she's going to pick one of them to be the best out of n choices. All right. So now that we've chosen the best, how many? Oh, I forgot to try my video. Sorry. Not that it really matters because I imagine of all the classes I do, these videos probably get watched the least. So now how many choices are there for second best? You know, I want you to tell me anyway.
-1.
Right. And then there are n-2 choices for third best. And so on all the way down to line and down the line until you get to there being 2 choices for last to best or last to worst and 1 choice left for whoever is worse. So there are n factorial, oh my gosh, n factorial possible. I was trying to say factorial and possible at the same time. I was trying to say factoriable, n factorial possible rankings. Yeah, interesting. What else are they asking here? Let's look at problem 30. Actually, let's look at problem 29. No, not that one. Let's look at 30. I think you guys know how to do this one. But these are good to look at. I know these are homework problems, but I also think it's worth. I feel like of all the things in this class, this topic is the most just like, it feels like it's coming kind of out of left field. It's like, okay, we're going to throw this thing on at the end. Yeah, there are reasons to know about it, like probability stuff, combinatoric stuff does come up in the world of biological sciences, but it feels very much like we've been doing all this other stuff and now we're going to tack this on at the end. And so it can be difficult to understand what's happening because it's kind of like we haven't really dealt with this. So I don't feel bad being very explicit about what's going on.
In biology, you don't use it that much.
Right, I would agree. So plant breeding. We have 5 males and 4 female plants. And when I'm reading a question like this, what I really want to do is not write down all the information. Like you definitely, when you're doing these problems, shouldn't write down the whole question unless you really think you need to. So I have 5 male and 4 female plants, and they're going to be arranged in a single row. You want to arranged in a single row. So already I know my single row should have how many spots? Well, right. We do a lot of this in counting and combinatorics, just writing out all your spaces to see what goes where. All right. To ensure breeding, no 2 male plants can be next to one another. How many arrangements are possible? So we want no males next to each other. Okay. Now, unlike the boy and girl problem he started off class with last Monday, this one's a little different, and we're not thinking about the boys sitting differently being a different combination, right? I don't care if the first male plant is here or the second male plant is here. That's the same as far as we're concerned, right? The plants are identical, for lack of a better word. Whereas people, definitely different, right? It matters if I sit here versus my brother sits here, right? We are different people. Maybe my wife wants to sit next to me and not my brother. So, right, that's kind of the difference, is we don't distinguish between the plants, whereas we definitely do distinguish between the people. All right, so how are we going to figure out how we can make these plants so that none of the males are next to each other? Well, I feel like this is kind of, I always struggle with these, to be perfectly honest. I feel like we want to just say, did you have something? Okay, no, I'm happy to take suggestions. So I always want to do this in the wrongest way possible, I feel like, which is not helpful. Right? I want to be like, okay, so I want no males next to each other, and I have 5 male plants. So actually, maybe we are supposed to consider these being different, because otherwise I think we only have kind of one choice, right? Because you have to have,
If you were to do it in real life, you just alternate between
right.
male and
You'd have to have male, female, male, female, male, female, male, female, male. Which seems like there's only one possibility. So I do have to kind of disavow what I said before, I guess, and that maybe these are all different types of male plants, right? Maybe they're not all the same. So if that's the case, how many ways can we arrange the 5 males? Well, I think it's 5 factorial. How many ways can we arrange the 4 females, assuming they're all different? I guess that's going to be 4 factorial. I suppose this question is better understood in the light of thinking of them as like boys and girls, like actual people, right? If I want to let 5 boys and 4 girls sit next to each other in a row, and I don't want any of the boys next to each other, well, then I have to do it boy, girl, boy, girl, boy, girl, boy, girl, boy. But maybe I want James, Daniel, Michael, Grant, and Duff sitting here. Maybe I want James, Michael, Daniel, Grant, and Duff sitting here, right? So there are definitely 5 factorial ways of arranging those 5 different boys. And similarly, there's 4 factorial ways of arranging those 4 different girls. Yeah, I don't feel great about this question, to be honest. Like, I think that's right, but it just feels, it feels like there's not always enough information. That's going to be, unfortunately, a common feeling when doing these problems, is you're like, am I missing something? Usually you're not, but it can be, yeah. So yeah, so I guess something to take away from this is leave your assumptions at home, right? I started this problem making an assumption. I was like, well, clearly the plants are the same. And then we got an answer that indicated that probably wasn't the right choice, right? Getting only one possibility doesn't seem very likely. What if we change the question? In fact, actually, let me grab it. Of course, I have millions of papers here. Yeah. Is that where I'm going? Sorry, one second. Sure, we'll come back to that. Let's look at a couple more homework ones. And then yeah, I like the homework problems. Let's look at, yeah. Cool. I'm going to change up some of these homework problems just so that you get more practice. So let's look at 32 amended. Let's suppose we toss 7 coins. 7's kind of a lot. Let's make it 5. The reason I want to do 5 is because we can actually write out 5. 7's like a lot of possibilities. 5's not too many. Suppose we toss 5 coins. How many ways can we get 3 heads? Well, there's an easy way to answer this question, but we're going to do it the long way. So when you toss 5 coins, as far as the number of heads resulted, right? If we're thinking about the number of heads, there are 6 distinct possibilities. You can get 0 heads, you can get 1 head, you can get 2 heads, 3 heads, 4 heads, or 5 heads. There's only one way to get 0 heads. You flip 5 tails in a row. I do think sometimes it's useful to think about when you're flipping coins, not just flipping 5 separate coins at once, but flipping them one after another. So you can think about each flip being kind of distinct from each other. So then if I want to get 1 head, there's actually 5 different ways to get 1 head. I can get the head first and then 4 tails, or I can get the head second, or the head third, or the head fourth, or the head fifth. There are 5 different ways I can get 1 head. There's going to be 10 different ways of getting 2 heads. Let's write them out. So I can either be heads, heads, tail, 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 or heads, tail, heads, tail, tail. So there is a way of organizing this, which I want to point out to you. The way I'm organizing this particular one is I'm starting with heads, heads, and then I'm moving the rightmost head over to the right as much as I can. So I'm going to move this over heads, tails, tails, heads, tails, and then heads, tails, 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 heads. And now I've exhausted all the possibilities where I have a head first. So now I'm going to move over and have tail, head, head. And then I'm going to keep doing the same sort of process. So then I'm going to move the rightmost head over 1. So tail, head, tail, head, tail. And then I move the rightmost head over another one. Tail, head, tail, tail, head. And then I'm done with all the ones where heads is second. So then I go over to heads being third, and then heads, and then tail, tail, heads, tail, heads, and then tail, 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 heads, heads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways. So now here's what I want to point out, because I really don't want to write this again. I mean, I'd fine write it again, but I really don't want to. The number of ways of getting 2 heads is the same as the number of ways of getting 2 tails. I could totally interchange every head and tail and say, okay, tail, tail, head, head, head. Tail, head, head. Right? I'm literally just flipping every head to a tail and every tail to a head. And that's going to give me all the ways of getting 3 heads, which should be exactly the same as the number of ways of getting 2 heads or 3 tails. So I don't want to continue writing this, but I will because I should. Right? This is the same number. And the same is true for 4 heads. The number of ways of getting 4 heads is the same as the number of ways of getting 1 head or 4 tails. I'm just going to say all the tails are heads now. So I could have tails, heads, 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 tails, sorry, heads, tails, heads, 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 tails, heads, 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 tails, heads, or heads, 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 tails. Right? All I did was took the 1 headers and switched all the tails to heads and all the heads to tails. And then finally, 5 heads is obviously going to be heads, 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 heads. Okay, now here's what I want you to see. The total number of possibilities. Well, the easy way to calculate it is to say there were 2 choices for the first flip, 2 choices for the second flip, 2 choices for the third flip, 2 for the fourth, and 2 for the fifth, to give you 2 to the fifth, which is 32. And if you count these up, 1 plus 5 plus 10 plus 10 plus 5 plus 1 is 32. Now, how many ways are there of getting 2 heads? Well, there are 10 ways of getting 2 heads. And 10 is equal to 5 choose 2. Which makes sense if we think about what we're doing. We're asking, if you flip 5 coins, how many different ways can you choose 2 of them to be heads? Okay, let's do the math though. 5 choose 2 is 5 factorial over 5 minus 2 factorial times 2 factorial. So writing it out, that's 5 times 4 times 3 times 2 times 1 over 5 minus 2 is 3 factorial. So 3 times 2 times 1. 2 factorial is 2 times 1. Cancel a 3, 2, 1. 5 times 4 is 20 over 2 gives you 10. And that will always work. In fact, each of these things is the number of ways of choosing that many things out of 5. So this here, that's equal to 5 choose 0. There's one way of choosing 0 things out of 5 things. This amount here, 5 is equal to 5 choose 1. There are 5 ways of choosing 1 thing from 5 things. I always feel like that's the easiest one to hear in your head. There are 5 ways of picking 1 thing out of 5 things. Well, yeah, of course, right? There's 5 things to pick. I can either pick the first, the second, the third, the fourth, or the fifth. There's definitely 5 different ways of picking one of them. This one here, this is 10 equal to 5 choose 2. This one here is 10 equal to 5 choose 3. This one here is 5 equal to 5 choose 4. And this one here is 1 equal to 5 choose 5. So a couple of things here. Oh, actually, in fact, the way the second half of this question is, how many ways can we get 3 heads? Okay. Oh, sorry, I answered 2, but it's the same as the answer for 3. Apologies. So the number of ways of getting 2 heads is 10. The number of ways of getting 3 heads is also 10. But here's the point. The question asks, or my version of the question is, how many ways can we get 3 heads? 10. And then we also ask the question, how many ways can we get 2 tails? Well, it's literally the same question. If I'm asking the number of ways to get 3 heads, well, if I flip 3 heads, the other 2 coins are tails. So if I'm asking the number of ways to get 3 heads, it's the same as asking the number of ways of getting 2 tails. It's also technically the same as asking the number of ways of getting 2 heads. And because heads or tails is kind of interchangeable. So the point here is that whether you're finding 2 out of 5 things or 3 out of 5 things, the result's the same. Essentially, if those 2 bottom numbers add up to 5, they're the same. So just as another example, more generally, n choose k is equal to n choose n minus k. If you want to know the number of ways of choosing k things out of n things, it's exactly the same as picking n minus k things out of n things. Or the way I see it, the reason that, say, 10 choose 3 is equal to 10 choose 7, if I'm trying to pick, say, 7 out of 10 people to be on a committee, instead I can just pick the 3 people I want to exclude. And the number of ways of picking people to exclude should be the same as the number of ways of picking the people that you want to include, right? If I can exclude 3 people in so many different ways, I can pick the other 7 people in the exact same number of ways. There is no other way. So that's kind of the way I think about it. I don't, yes, I don't mean it in an exclusionary way. In fact, honestly, please, if you're picking people to be on a committee, exclude me. I don't want to do that extra work. They're the lucky ones. They don't have to be on the committee. But yeah, we're not picking them. It's the nature of these math problems with choices. You have to pick people to not be on the committee. They can be on their other committee. Yeah, I'll say it that way next time. So then I like this follow-up question, question 33. Again, we're going to toss 5 coins. I feel like toss feels so careless. I can just toss coins everywhere here and there. I'm going to flip 5 coins. And now I want to know how many ways to obtain at least 3 heads. Well, we actually know the answer because we did the work. If you look back here for just a second, there are 10 ways to get 3 heads, 5 ways to get 4 heads, and 1 way to get 5 heads. So we could say, well, we know it's going to be 10 plus 5 plus 1. But more generically, if I'm tossing 5 coins and I want the number of ways of getting at least 3, well, it's going to be the number of ways to get 3 plus the number of ways to get 4 plus the number of ways to get 5. Or as I don't remember which notation he's preferring in class, he would probably write this as C5-3 plus C5-4 plus C5-5. Oops. Right, I think that's how he writes it. I don't actually like. I've seen him write like 5 different ways. I feel like so. I would default to this. What if I said, how many ways to obtain at most 2 tails? Well, is at least 3 heads the same as at most 2 tails? This is where the language, I feel like we have to parse it somewhere. At most 2 tails, what does that mean? Well, I could have 2 tails, or I could have 1 or none, right? But be careful. People kind of, I always like at most. Okay, most means that's the most I can have. Okay, so at most 2 and then 1 or 0. So having 2 tails is the same as having 3 heads. Having 1 tail is the same as having 4 heads. Having 0 tails is the same as having 5 heads. So it's literally the same thing. At most 2 tails is the same as at least 3 heads. I don't know if we get to the binomial or not. Like, I mean, we're kind of circling around it at this point, but I don't feel like we get so much into the like n choose k times p to the k times q to the 1 to the n minus k formula. Like, I don't think we do that quite as much, but it's there. It's kind of sitting there already. I just don't think we're super explicit about it. Sure. So 5 choose 3, right? So we can actually calculate this. Right? This is equal to, so 5 choose 3 is the 5 factorial over 3 factorial times 2 factorial. The 5 choose 4 is 5 factorial over 4 factorial times 1 factorial. And the 5 choose 5 is 5 factorial over 5 factorial times 0 factorial. Oh, because so the previous question, fair point. So the previous question, we said, how many ways can we get 3 heads? So that question, although it doesn't say it explicitly, it is heavily implied they mean exactly 3 heads. So this doesn't say at least 3 heads. This says how many ways can we get 3 heads and not more. I know those words aren't there, but you kind of have to pretend like they are. So if someone means at least, they should say the words at least. If someone doesn't mean at least, then they won't say. But typically, no one's going to say how many ways can we get exactly 3 heads. They're going to say how many ways can we get 3 heads and assume that you know that we mean exactly 3.
They'll say more than.
Right.
And then you have to do it like what something minus whatever.
Right. So if it's an at least or an at most or something like that, they will use the words to give you that. And if it's not that, they won't use any words. You just be like, oh, they didn't use any extra words, so they mean just this. But yeah, that's a really, really excellent question. Let me ask you another question just while we're on the subject. What's the probability? Not the probability, we're not there yet. What's the, if I flip or toss 20 coins, how many ways to get at least 2 heads? Oh, sorry, you want to see the words. And reading this question, you might think that this seems pretty annoying. At least 2 heads. Okay, so that's going to be the number of ways of getting 2 heads plus the number of ways of getting 3 heads plus the number of ways of getting 4 heads plus all the way to the number of ways of getting 19 heads plus the number of ways of getting 20 heads. That seems kind of terrible. So here's what we can do instead. You can say, well, first, you could do this, right? You could do 20 choose 2 plus 20 choose 3 plus 20 choose 4 plus 20 choose 5 and on and on and on and on. But there's a better way. So first off, how many total possibilities are there? When we flip or toss 20 coins? Well, just like before, when we flipped 5, there were 2 times 2 times 2 times 2 times 2 possibilities, because each flip you have either a heads or tails possibility. So when you flip 20 coins, how many possibilities are there? Two to the 20th power, which is a pretty big number. It's like 1 million-ish. A little bigger than 1 million, actually. Okay, so I want to find the number of ways of getting 2 or 3 or 4 or 5, all up to 20 heads. But I don't want the number of ways of getting 1 head or 0 head. So here's what I also know. All these things here together, the number of ways of getting 0 heads, plus the number of ways of getting 1 head, plus the number of ways of getting 2 heads, plus all the things in between, all the way up to the number of ways of getting 19 heads, plus the number of ways of getting 20 heads. Those are all the ways, right? One of those things has to happen. You flip 20 coins and you either get 0 head, 1 head, 2 head, et cetera, et cetera, et cetera. So all these possibilities have to add up to 2 to the 20th power. And I can't help myself. I have to say this thing right now because it's just so neat. When you add up these numbers, what you're adding up is 20 choose 0 plus 20 choose 1 plus 20 choose 2 all the way to 20 choose 20 equal to 2 to the power. That's something that's kind of just cool. If you add up all these, okay, all these binomial coefficients. So if you've ever like multiplied out like x plus h to the 3rd, because you were doing some limit definition of the derivative and trying to find the derivative of x cubed, and you multiply this out and you got x cubed plus 3x squared h plus 3xh squared plus 1 h cubed. So kind of familiar, vague. It's probably like 17a. Well, here's what you are really doing. You have 3 choose 0 times x cubed plus 3 choose 1 times x squared h plus 3 choose 2 times x h squared plus 3 choose 3 times h. And so if anyone ever asks you to multiply out something gross like x plus h to the 5th, it's exactly what you think it's going to be. It's going to be 5 choose 0 times x to the 5th. plus 5 choose 1 times x to the 4th times h plus 5 choose 2 times x to the 3rd times h squared, and so on and so on and so on. That's where people actually find those coefficients. It's kind of neat. Also, they show up in Pascal's triangle. You ever seen the 1, 1, 1, 1, 2, 1, 1, right? That whole thing. That's those numbers also. They show up everywhere. They're super cool. I can't help it. They're really neat. Yeah. So back to this. We're trying to find that quantity there, right? This is the number of ways to get greater than or equal to 2 heads. Well, I can calculate that really easy. I know that you should have heard earlier today, they're making all sorts of like really loud noises in this building, around this building. How many ways are there of getting 0 heads if I flip 20 coins? One way. It's always one. So if you ever ask how many ways can you get 0 something, it's always one way. Because whenever you do something choose 0, right? 20 choose 0. Yeah. Anything choose 0 is 20 factorial over 20 factorial times 0 factorial. The 20 factorial is canceled and 0 factorial is 1. So we get 1. So anything choose it, right? If you're trying to figure out the number of ways of getting 0 heads, there's one way. And then the number of ways of getting 1 head is going to be 20 choose 1. Either your first flip was a head, or your second flip was a head, or your third flip was a head, or so on and so on and so on. And that's going to equal 20. So the thing that I want, the number of ways to get at least 2 heads, is equal to this number here minus these 2 numbers here. Two to the 20th power minus 1 minus 20. Or if I simplified it, 2 to the 20th power minus 21. This whole idea is the idea of what's called the complement. If you're being asked to find something and it looks terrible to calculate, instead take the entire value of all the things that can happen and subtract off the things you don't want. It's a really useful thing. Yeah, 158. Okay. Sorry, I got kind of distracted there. Were there any other problems in this section we should look at? 12.2. Wow, there's a lot of questions from 12.1. Sorry, I said 12.2. 36. Ooh, that looks terrible. That looks kind of fun. So, it looks fun, but let's move on this time. Sorry, I'm always. Ooh, yeah. Okay, 40 is a good one. Something we've already said. Prove n choose k equals n choose n minus k. This shouldn't be too bad. We know the formula. What's the formula for n choose k? N choose k equals n factorial over what? N minus k factorial, and what else? Yeah. All right, well, let's get n choose n minus k. Here's where we should be very specific about writing this. So if I was writing this, I would write it the fast way. I'm gonna do the slow way. So n factorial over n minus k factorial, and then n minus k factorial. But those are definitely the same, right? Because n minus k is just k. And that's definitely equal to that. So I don't think that problem is too horrendous to have to do. But you do have to write out something. You can't just be like, well, they're equal, obviously. Like you have to write things that show. And the key step, I think, is remembering that, oh, when we do this, this should be n minus whatever is actually down there, right there. Just like here, it's that. let's look at 42. So I think it is worthwhile. So we have a group of, I'm going to change the numbers. We have a group of 8 males and 12 females. And we want to play doubles tennis. So 2 men, 2 women are to play each other. In a men versus women doubles match. Okay. I feel like that's, I don't actually know because I don't really watch tennis, but I feel like that's usually not the way the doubles go. I feel like it's a man-woman versus man-woman, but whatever. I don't care. The women win. How many different ways can the match be arranged? How many ways? Okay. So if there are 8 men to choose from, how many different ways can we make the team that's the men's side? Does order matter? Does it matter if I pick player 1 first and player 2 second, or player 2 first and player 1 second? Am I still going to get the same team on that side? Yeah, order doesn't matter here. So if order doesn't matter, what are we thinking? We're thinking not the permutations, but the combinations. I always say choose, but combinations is also the right word to use. So I'm thinking, well, for the number of ways I can pick the men, it's going to be 8 choose 2, or how many ways you get 2 I can't say it with combinations. 8 choose 2. It's the number of combinations of 2 men out of 8 men. All right, how about for the ladies? For the women, it's going to be 12 choose 2. Same reason, right? There are 12 women to pick from. We're going to pick any 2 of them. There are 12 choose 2 ways of doing that. But then we have to multiply them together, right? Because maybe these 2 men play these 2 women, or maybe these 2 men play those 2 women, right? So each pair of men has to get paired with each pair of women. So we multiply them together and get something. Interestingly enough, people also phrase this as like the handshake question, meaning if there are 8 people in a room, how many handshakes are going to occur if everyone shakes hands with everyone else? Well, it's literally 8 choose 2. You're finding all the ways you compare 2 people, but it doesn't matter which ones you pick first. So if you're doing 8 choose 2, it's literally going to be 8 times 7 divided by 2. 12 choose 2 is 12 times 11 divided by 2. I'm cutting out the middleman there, right? 8 choose 2 really, 8 factorial over 6 factorial times 2 factorial. But that's just 8 times 7 over 2. Same deal here. So that's 5628 times 66, which is something. I do want to point this out because I think it's worthwhile. If you had 8 people in the room and you want to find all the ways you could pair them together, well, take the first person, pair them with each of the other 7 people. You're done with them. Take the next person, pair them with each of the remaining 6 people. Done with them. Take the next person, pair them with each of the remaining 5 people, and so on, and so on, and so on, and so on, and so on. That number is definitely equal to 7 plus 1, choose 2. When you add up the first so many integers, you get that number plus 1, choose 2. Kind of a neat formula. It's really just the triangular numbers formula, which I feel like you might have seen this before when you're talking about integration. This is right. If you want 1 plus 2 plus 3 plus 4 all the way to n, it's just n times n plus 1 over 2, which is just n plus 1 choose 2. Okay, I said enough. I said too much. 204. I should stop talking. I should have stopped talking 4 minutes ago.